Welcome everyone. This is our February STLE Alberta section meeting with the presentation on tribology of diesel engines presented by Michael Holloway. And we are in partnership with SAE Alberta. Please note, Michael was not able to join us at this moment. Something has come up, but we do have his recording, and so I'll be playing that. Any questions, I am going to ask that you put them into the Q&A, type them in there, and Yutong has offered to take those down and who's asked the question, and we'll make sure that we get Michael tied in to answer those for you guys. So I apologize for that. Because it was last minute, we didn't want to cancel anything, and because I have a presentation, so we will continue on. Here's our list of our executive. As always, we do have some open positions, as well as we welcome additional people just to step in and help out and give ideas and suggestions. Please contact any one of us. So next month, we have Craig Winterfield presenting on SEM EDS Advanced Wear Debris Analysis for Optimized Maintenance. Please note that is actually on a Wednesday as opposed to a Tuesday. Still the same time, but a Wednesday. And we may get Ralph to actually maybe present on April 26th. We'll see about that. And then on May 17th, we have a presentation on open gear lubricants presented by Fuchs. I'm not sure if you've probably received, or maybe all of you received emails from STLE head office regarding the STLE digital badging. So please note, you can actually download that and put that onto your signatures and other places that you want to put it, LinkedIn. Alberta, we are looking at doing a certification training on OMA or CLS, or maybe both. There was a survey that was sent out. If you guys have not responded to that survey, it'd be great to get some additional responses. I think we've only got about 14 responses right now, and that's not giving us a clear idea of what to proceed with. We are trying, as I mentioned at our last meeting, we're not looking to make money on this, and even if we have to fork out a little bit, we are okay with that, but we do need to make sure we have a decent attendance and what you guys are interested in. So definitely respond to that survey. I'll also get it sent out again today. Alberta section, our websites, LinkedIn and YouTube. So the recordings of these presentations are put onto YouTube as well. So if you're happen to miss today's, you definitely, or you want to re-listen, you can definitely go there. Please confirm that you are on mute during the presentation. If you have any questions, please note that there is a chat and a Q&A option. For today's questions, please use the Q&A just so that we can keep track of all of them. The executive are monitoring those, and please note that it is being recorded. So Michael Holloway has over 35 years experience in the industry. Michael started Fifth Order Industry as a business for competency development and CLS, OMA, and ICML certification preparation. From 2013 to 2019, he worked for ALS Tribology. In 1999 to 2013, he served as director for NCH Corp. Prior to 1999, Holloway worked as an applications engineer, OEM specialist for General Electric Plastics, Roman Haas Electric Chemicals as a production engineer, and as an aerospace materials engineering chemist for W.R. Grace, and as a polymer research chemist for Olin Chemical. Holloway served as the North Texas Section Chair and Condition Monitoring Chair for STLE, as well as a certification examiner for the International Council for Machinery Lubricants and adjunct professor at the University of North Texas. Holloway also has numerous certifications, including the STLE, CLS, and OMA, and all 8 ICML certifications, and the CLGS through NLGI, and holds the U.S. patent 7241723, bearing cleaning composition and method of use, 2007, and is the author of 9 industry-based books. Tribology of diesel engine is today's topic. Diesel engine is arguably one of the most important machines invented, from mammoth system to power ships, the generators used in locomotives and engines of transportation of freight and people, to heavy mining and construction equipment. The diesel engine is responsible for all as well as generally electrical power to the grid. These engines have been used in aircrafts as well as race cars with limited success. The science of tribology can also be completely explained through exploring the workings of diesel engines. This seminar looks at the lubrication regime, wear, contamination, oil function, oil chemistry, and failure opportunities of a diesel engine, with the goal of providing a thorough example of tribology. There are a dozen lubrication certifications to achieve through STLE, ICML, and LGI. Each certification has its purpose. In our presentation, you will understand what they are, and I shall stop right there, and we'll kick over to the next part. We'll share. Okay, see if I can get the tribology one going now. All right, here we go.
We're looking at the tribology combustion engines. Now, the diesel engine is arguably one of the most important machines invented, from mammoth systems that power ships and generators used on locomotives, and the engines of transportation of freight and people, to heavy mining and construction equipment. The diesel engine is responsible for all of this, as well as generating electricity to the power grid. These engines have been used in even aircraft as well as race. Well, in our case, in terms of lubrication, gasoline engine oil typically doesn't get analyzed in laboratories compared to diesel engines and natural gas engines. Now, dare I say that gasoline engine oil is probably the largest volume product produced, only because there's the most amount of vehicles on the road. Well,
I'm being told that you guys can't hear. Is that true?
When you're on mute, Jacqueline, we can't hear, but there should be a way that you can share sound as well.
Share sound. Let's try this again. Sorry about that.
Trace it.
Does this sound better?
There are not too many people out there that'll take their gasoline engines and have the oil analyzed, and you should, by the way. But you don't. You just change it according to whatever the service tells you to do.
I'll just restart this. Sorry, everyone.
We're going to look at the tribology combustion engines. Now, the diesel engine is arguably one of the most important machines invented, from mammoth systems that power ships and generators used on locomotives, and the engines of transportation of freight and people, to heavy mining and construction equipment. The diesel engine is responsible for all of this, as well as generating electricity to the power grid. These engines have been used in even aircraft as well as race cars, with limited success. The science of tribology can almost be completely explained through exploring the workings of a diesel engine. We're going to look at the lubrication regimes and various wear and contamination, oil functions, and even oil chemistry and the failure opportunities, and then get into a little bit of oil analysis of the diesel engine, with the goal of providing an example for tribology. We look at diesel engines, gasoline engines, natural gas engines. We're going to focus mostly on diesel engines, and you know why? Because it's going to be where the lion's share of all the oil is used. Now, some people would argue it's gasoline engines. Well, in our case, it's in terms of lubrication. Gasoline engine oil typically doesn't get analyzed in laboratories compared to diesel engines and natural gas engines. Now, dare I say that gasoline engine oil is probably the largest volume product produced, only because there's the most amount of vehicles on the road. But let's face it, there are not too many people out there that'll take their gasoline engines and have the oil analyzed, and you should, by the way. But you don't. You just change it according to whatever the service tells you to do it, 5,000, 7,000 kilometers, 10,000 kilometers, 7,000 miles, whatever. But let's focus on diesel engines, because a lot of the same concepts and chemistries that are occurring in the diesel engines, we can translate over to natural gas and gasoline engines in some cases. Not always, though. Obviously, they're different, very different animals, and they do have their different considerations. Now, in terms of the basic principle operation for a four-cycle engine, four-stroke, some folks call it, is a gasoline engine. We're going to have the intake stroke. Here, the piston moves down, intake valve opens, air is drawn into the cylinder by a pressure differential. And then we're going to have our compression stroke. Here, the intake valve closes, and then the crankshaft rotates, the piston moves up and compresses that air, if you will, air-fuel mix. Temperature rises, actually air mix. The temperature rises and increases significantly. Then we're going to have a power stroke. The fuel injector fires and fuel ignites just as the pistons reach almost the top dead center on its travel. And expanding gases, which result from the burning of the fuel air mix, forces that piston down into the crankshaft. And then the exhaust stroke. And after the dual charges burn, the exhaust valve opens and burned gases are forced out of the cylinder by an upward movement of the piston. And it starts all over again. Now diesels, they're two-stroke, they're not four-stroke typically. And there are two types. A lot of folks never realize this, but there are actually two types of diesel engines. There's the trunk piston engine that's used quite a bit in marine applications, and the cross head piston style. I'll go into a little details about these, but you can see by the configurations it's a bit different. And you'll actually see the crosshead piston engine. Not only is there's some side thrust going on, but we have a crosshead guide and the guide shoe and the crosshead and the piston rod. These things are going to be having to be lubricated as well, as opposed to the trunk piston engine configuration where we have a connecting rod, the main journals and so forth. They're going to be lubricated. Now the trunk piston, an internal combustion engine, in this case obviously, in which the connecting rod is directly connected to the piston by a pinion and guinea pool, also called a piston pin. That comprises of the piston with an elongated skirt and that absorbs the side thrusts and is attached to the connecting rod by a small end rotating bearing. This is used in small four-stroke engines as well. The crosshead piston, that comprises of the piston crown, the piston skirt and piston rod, is used in large two-stroke engines, which is connected to the crosshead functioning to transfer the side thrust to the engine structure. The combustion engine lubrication, the principal engine oil functions. Well, there's to reduce friction, minimize wear of the engine components, including corrosive wear. We're going to remove heat, so it's going to have to act like a coolant. That's one reason why there's oil galleys running through the engine block and so forth. We're going to protect these engine components against some harmful deposits. And it's going to act like a seal. That's going to happen at the ring line. A lot of folks never consider engine oil as a sealant, but it is. It forms a dynamic seal. Now the chemistry functions. We have to control viscosity. Obviously, viscosity is the #1 characteristic to concern ourselves with, but also alkalinity retention. Its ability to neutralize acids as they build up. As we remember, when oils start to break down those molecules, they become free radicals. They become radicalized. And then they begin to propagate and start grabbing onto other things. And finally forming a huge molecule. If we can thwart that scenario to inhibit the acid formation through alkalinity retention, we can reduce the oxidation potential that's occurring. The oil chemistry is also going to have to keep things clean through detergents and dispersant formularity. That's going to help us control some insolubles. These insolubles, think about this. An insoluble means it's not soluble in a fluid. In this case, maybe in an oil or fuel or whatever. The idea is that those are hard particles that could form deposits and nucleation sites for worse problems down the line. So we're going to control that. It's also got to control wear. As we're going to see in these configurations, there's a multitude of different surfaces occurring where we're going to have to control this. And then we're going to obviously have oxidation stability to reduce the buildup. And then nitration stability. where nitric acids form and they begin a whole process of developing deposits. So oil function, in this case, first thing we'll take a look at is the main bearing. The thing that's holding the cam in place. The idea is that the oil function of the main bearing is to cool and to lubricate. The oil function of the crank pin bearing is also to cool and lubricate. Oil function of the crosshead and crank pin bearings here, once again, cool and lubricate. I can see lots of different moving surfaces here. Be it the piston pin, the bushings, and the connecting rods. Crank pin, the bottom end of that bearing, it's in the rotary motion. Now the cylinder line of the piston rings, lubrication, wear control, sealing, cleaning, acid neutralization. We can actually see here where the compressor ring, the wiper ring, and the oil ring. Now, see where that film is on the cylinder wall? You're going to notice even above it is a film of oil. That gets burned off over time. It's natural, especially in the diesel engine. The crosshead, conrod, and the shoe lubrication, once again, another surface to be lubricated and protected. You see where the piston rod is or the crosshead pin. Right in there, we're going to have a film of oil protecting. And our thrust bearings configuration, some mechanical drawings, give you an idea what these things actually look like. We're going to have it's going to be lubricated right there. You can actually see the lubrication hole. It's going to be bringing the engine oil in to lubricate. Here's some pictures of these things pulled apart. The main bearing, the thrust bearing, the journal bearing. Oil function of the camshaft, drive gears, exceptionally important. No one ever really considers the fact that a motor oil is also got to act like a gear oil. In this case, it does. It's cut away of a Series 60 Detroit diesel off to the left. On the right here is another way. It's a V8 right there. But the idea is, look at all those gears. They all have to be lubricated. You see a lot of dissimilar metals in there too, as well as these bearings. Now the cam roller, the roller guides. Obviously, there's lubrication having to be at here, right there on the surfaces as well. Constant lubrication. You also notice some dissimilar metals down there. Now the exhaust valve gear, valve shaft. Here we're dealing with hydraulic functionality as well as lubrication. So the engine oil actually has to pressurize and actuate those valves, as well as act as a gear lubricant. Especially in the exhaust valve shaft and the valve guides here, hydraulic and lubrication functionality as well. You can actually see where the valve guide is, you know, the stem seal and the spring too, but where the valve guide is. Even in the fuel injecting pump, where it's actually got to lubricate and seal too. Now the piston rod stuffing box. You see off to the left there, it's a whole series of glands and whatnot. We've got to actually, it's a bit of a Lambert, if you will. We're dealing with the lubrication as well as sealing too. Now, one of the most ignored componentry in an engine, unfortunately, in my opinion, for what it's worth, probably not worth a whole lot, but the oil function of a turbocharger, the rotor bearings in there. The turbocharger can heat up to about 1,000 degrees Fahrenheit. I've seen these things running red hot, not only on my vehicles, but Also on some others as well. These things, when I say red hot, you turn off the lights and you're revving that thing. Those things do get very, very hot. The motor oil, engine oil, if you will, is lubricating the radial bearings and the thrust bearings as well, getting incredibly warm. Now keep in mind, turbocharger bearings are spinning anywhere from 50 to 100,000 RPMs. You can't find a piece of diesel equipment these days without a turbocharger on. If you do, good luck. It's probably not worth a whole lot. The idea is that these turbochargers do force air down the combustion chamber, increases your horsepower, efficiency, and whatnot. But the idea is that these bearings are just absolutely abusive on engine oil. The oil function also in the tie rods. Here, a little bit different than lubricating per se. These things are actually acting to dampen the vibration and shock on the block. You get an idea what some of these things actually look like. And also, axial torsional vibration dampers. I don't know if you ever realize that, but that metal plate that's on the end, that's a torsional damper. And here, the oil's got to act as a cushion, if you will. Dampen that kind of shock that's going on as well. If we can reduce the vibration, we can reduce some shock load on bearings and sliding surfaces. We can extend out the life of the components. In terms of the turning gear, here's an idea once again that engine oil's got to act like a gear lubricant. Talk about a multifunctional fluid. Give an idea there. You actually see some spur gears, worm gears, all kinds of different gearing going on here. You'd be hard pressed to look at an engine and not find any particular type of lubrication regime or componentry in there. Heck, you got all different types of gears. You got sliding surfaces. You got pistons. You have pumps. You have all kinds of stuff going on. Engines are amazing. They're a great examination of everything tribological there is. Here's an example of engine hydraulics. It's actually pressurizing. Just wanted to put that up there so you can take a look at it. It's kind of a cool little diagram. Now, combustion engine lubrication requirements. Different physical properties and performance levels are required for different lubricants depending on their applications. Therefore, oil degradation is dependent on lubricant type and applications. Crosshead engines generally burn residual fuels. In this type of engine, separate systems are used for either cylinder lubrication, that could be a total loss system, crankcase lubrication. And different properties are required for oils used for these two different types of applications. We look over here at the functionality, the wear control, be it on the rings and liners, thermal oxidation stability, piston deposit control, rings, grooves, lands, undercrowns, our detergency, dispersancy, engine cleanliness functionality, our alkalinity reserve, even water separability, because keep in mind, some of these engines are going to be used in marine. Rust inhibition, filterability, free of gelling tendencies, load carrying property of reduction gears, load carrying property of valve train areas, and even load carrying property of hydraulic functions. Once again, these engines got all kinds of stuff going on in them. Now, cylinder oils, in this case, one of the most important properties of the cylinder oil is the high alkalinity to combat the corrosive and sulfuric acid. Those are derived from the combustion of free sulfur in that fuel, especially marine fuels. This sulfur can be up to 5% in certain cases, which is unfortunate. So we can actually see in cylinder oils and whatnot. It's important. Wear control, thermal stability, piston deposit control, detergency, rust inhibition, filterability is not necessarily so much, but you have to do free gels. Now, system oils, the crankcase and the crosshead engine is separate from the combustion side. The division is achieved by a piston on the rod gland, although in principle the system oil is not directly exposed to contamination by combustion byproducts or used cylinder lubricants. In practice, some leakage and contamination through the piston and rod gland does happen. You know, in addition, while some of these crosshead engine designs with water-cooled pistons still exist, most recently introduced models have pistons cooled by the system oil itself. Now, system oils, they possess a degree of alkalinity reserve together with dispersive properties. System oils used in engines with oil-cooled pistons may be exposed to high piston undercrown temperatures. And in these circumstances, enhanced thermal and oxidative properties of the system are also required. Such alkaline system oils, they have the advantage that, well, they can protect the internal engine parts against corrosion by strong acids, which can alter the oil by leaking of used cylinder oil and draining through the piston rod glands. Now the dispersancy, those properties, they minimize sludge deposits and keep the piston and undercrown piston under space, the cushion gland and whatnot, and the crankcase keeps it all clean. And notwithstanding, these properties such as oils are usually designed to have good water and sludge separation properties so that water and sludge contamination may be readily removed by normal purification methods. Normally, system oil is not designed for an oil change at regular intervals here. Then we have medium speed trunk piston configurations. Here, medium speed trunk piston diesel engines employ a single lubrication system for the entire engine. However, in certain instances, these cylinders are also fitted with lubrication coils through which oil is actually fed through. Nevertheless, in these cases, splash lubrication also contributes significantly to the amount of oil on the cylinder walls. Whilst the need for extreme pressure agents and anti-wear properties is less marked than, say, for the high-speed engine configurations, these properties are often incorporated in order to widen the shipboard application in the case of marine, and the class of oils and other equipment and reduction gears. Now, multi-grade oils find little application in this class of engines, so we're going to be straight weighted up. Now, we're going to say some medium speed trunk piston engines burn distillate fuel, and the lubrication requirements are similar to those for high-speed trunk piston engines burning this type of fuel. But most medium-speed trunk piston engines normally designed to burn residual fuel containing sulfur, maybe up to 5%. Now, with the new regulations, that's going to be changing. The need for crankcase lubricants with an appropriate level of alkalinity is still important, though. Having a high base number to neutralize those corrosive combusted acids that could contaminate your oil. Medium speed trunk piston engine oils contain additives imparting a high level of oxidation and thermal stability, a lot of detergency, a lot of dispersancy characteristics. They protect against corrosion in both the ferrous and non-ferrous materials that are going to be found throughout this engine. And they're going to have anti-foam characteristics as well. Medium speed trunk piston engine oils generally contain relatively little or no ash dispersant additives, since they can be negatively affecting any kind of water separation performance. In this case, the crankcase oil in these tube piston oils continuously exposed to combustion products, apart unavoidable indirect contamination. The system oil in the crosshead diesel engine is not necessarily. Now, the alkalinity reserve of the new lubricant is selected on basis of engine design, the sulfur content of the fuels to be burnt, and the consumption rate. The latter is determined typically primarily by the engine design and then by operating conditions. It's well known that the base number provides additives that also give dispersancy detergency in the oil. In addition, certain alkalinity additives also contribute to the antioxidative capacity of the oil as well. It's important to observe the base number of the oil. If you're going to be analyzing it, you should be analyzing it. Its neutralization capability. You know, the trunk piston engine burning residual fuel should be fitted with a centrifugal purifier or separator as well. It helps clean out the lubricating oil. Under normal conditions of oil consumption, trunk piston engine oils, they don't require oil changes for a very long time, perhaps up to several years in certain cases for larger engines, provided that you have the centrifuge capacity is not too small and kept in correct operation, maybe that the combustion conditions are normal, and the oil is not contaminated with raw residual fuel, and the trunk piston engine oil is therefore required to have at least moderate dispersancy properties and excellent water separation characteristics. In this case, the high-speed piston engine oils, they employ a single lubrication system for the entire engine. Their lubricants must be capable of working under adverse conditions that can promote oxidation, nitration, and thermal breakdown of the oil. And that can lead to oil contamination, so especially by certain other combustion products. These corrosive products, they might be present in the oil, resulting where they actually start to form oil oxidation with weak acids that can corrode the bearings in particular, and the strong acids, the combination of sulfurous fuels. Now, strong acids are corrosive to a lot of ferrous compounds, such as the cylinders and piston rings. Now, you want to provide satisfactory lubrication under these conditions. The crankcase oils must contain detergents, dispersants, alkalinity reserve, and Antioxidants, anti-foaming agents, pour point depressants, and even anti-wear additives for valve trains are also commonly used. Multigraded oils are occasionally used in these things for maybe the smaller high-speed configurations. They usually contain the polymeric viscosity improvers as well. Some more of the lubrication requirements for the trunk piston and the crosshead. If we take a look at the fuel type that's either used or the key treatment systems, the dispersion properties, and the water separation oil changes, with the high-speed trunk piston engines, yeah, they use distillate fuels, and they're going to go through a filter, but they should have excellent properties in terms of dispersancy. And typically, though, they can easily emulsify, unfortunately. We want to be renewed on a regular basis in terms of changing. Now, as far as the medium speeds, they're going to use residual fuels. And typically, these things are going to be filtered with a centrifuge or cartridge filters or spin filters. The dispersive properties of lubricants are moderate. Their water separation should be excellent. And they don't necessarily need to be changed, once again. But the crosshead, these system oils, they obviously going to see some introduction of some residual fuels. And they also use the centrifuge and the filter. And they do have moderate dispersant properties of other lubricants. They're also going to need excellent water separation tendency. And they're not going to be necessarily changed. Give you an idea of the diesel oil, how it degrades. Now we see through oxidation and nitration. We talked a little bit about insolubles and these things as the oil starts breaking down and building up these macromolecules, these huge molecules that are insoluble, very chemically stable. Unfortunately, they hurt us because they can also start developing wear in our system. We could actually start seeing some wear metals come out too. And then deposit formation. Blankets the metal, increases operating temperature, unfortunately. Changes the configuration, the tolerances. Now, critical areas of lubricant performance include viscosity control, alkalinity retention, engine cleanliness control, insolubles control, wear protection, oxidation stability, nitration stability. These are the performance criteria required for diesel engine oil. I want to share with you specific lube oil consumption, which is the oil consumption in grams per kilowatt hour. The idea is the oil consumption of conventional piston engines has been between 1 and 1.5 grams per kilowatt hour. However, new engine designs have lower oil consumption, typically down to 0.2. And this reduction of oil consumption results from the incorporation of some special rings. The lower oil replenishment, lower top-up, is a direct consequence of lower SLOC. And incorporates different things. For instance, special rings, which are inset into the upper part of the cylinder liner. These special rings are described as either flame rings, anti-polishing rings, carbon cutting rings, burner rings, piston cleaning rings, so forth and so on. Such special rings installed at the top of the cylinder liners give a controlled clearance with the piston crown. Consequently, that crown land deposit is reduced to the extent that when the piston tilts during thrust and anti-thrust motions, the rubbing of the crown land against the cylinder liner surface is minimal. So bore polish caused by carbon buildup is prevented with less or no bore polish at all. And with significantly reduced hot carbon wiping in the cylinder liner, the oil consumption will be significantly reduced. And that's important. With less or no bore polish and with significantly reduced hot carbon wiping and cylinder liner, the oil consumption will be significantly reduced. I'm going to write that down, especially if someone's going for their CLS. Another explanation of reduced oil consumption is the improved gas sealing of the ring pack against the cylinder liner due to some better distribution of gas pressure from the back of the piston rings. This improved gas distribution is a direct consequence of a cleaner piston crown brought about by the application of these special rings. The reduced oil consumption will directly influence oil degradation through reduced oil top-ups. This will be reflected by an increase of viscosity, maybe a reduction in base number. Therefore, considering all parameters, The oil consumption must be seen as the key factor influencing oil degradation. The combustion engine lubricant failure modalities. We have engine power. The root here is that the kilowatt hour per gram correlates with the oil properties. In this case, maybe the base number determines oil drain intervals. You can measure that using an oil stress factor. If you want to know a little bit more about that, I can talk to you as well a little bit offline. It's kind of an interesting equation. We can determine this through oil analysis. The consequence here is the increase in kilowatt hour per gram of oil gives reduced oil life, unfortunately. Then we look at contamination. Gaseous, liquid, or particulate, be it through the air, combustive gases, reaction products, water, fuel, cylinder drains, dust, wear debris, soot. We're going to have an effect on the lubricant, be it air entrainment, oil degradation, change of viscosity. Some of the detection limits. If we're looking at the contamination through gases, we can actually see how this can impart. If we take and test the oil on air release and foam testing, or run it through the FTIR to identify these constituents. We can identify some liquid contamination in the case of water using the Carl Fisher, or even ICP in terms of identifying certain minerals that might be found in water. If it's liquid fuel, well, the flash point, gas chromatograph, the GC, the FTIR, and viscosity differences as well as VI, and even insolubles. The cylinder oil drains, where it can actually have an increase in viscosity and base number. Here, obviously, we're going to be testing the base number and the viscosity. That can bring about bearing problems. Check out those consequences on the engine. See, every failure opportunity we have here, we can test for it, detect it. We know the effect on the lubricant, but we also know the significance and consequences on the engine. In terms of particulate, dust, wear debris, and soot, here we can keep an eye on it with ICP to detect it, and insolubles and particle count. In the case of wear debris, ferrography is always really important. You can use particle quantifier index, PQI, very inexpensive test to run alongside the ICP. We get into the oil analysis, we'll understand that a little bit more. Pretty powerful tool. In terms of soot, it be a change of viscosity, thickens up the oil. You can actually check for insolubles. You can actually check for FTIR and soot meter as well. It's going to have an impact on the filter life. Now we have thermal degradation. In terms of heat, the root volatility. Oil thickens up, the volatiles. The oils typically you're going to have a molecular weight distribution, so some of the fines, lower molecular weight molecules within the oil formula is going to flash off to be volatilized. Here we're going to take a look at the NOAC. Make sure that you have a low volatility as much as possible. You can see a change in viscosity, obviously, because when the oil molecules are small, the lower ones are flash off, the viscosity is going to increase. It's going to accelerate some additive depletion, unfortunately, though, through oxidation. We can keep an eye on that. One thing that we're going to talk about at some point, we should talk about it now as well, is the ruler test for detection of these things. You know, the ruler test uses sweep volumetry. I know the rule is a trademark from a corporation, but it uses sweep volumetry. Great idea to keep an eye on additive depletion in terms of oxidation. Keep it in terms of thermal degradation due to hot surfaces. It brings about oxidation as well. We'll be able to look at it with FTIR, viscosity changes, acid number generation, and once again, the sweep volumetry of the ruler. These things give a great indication of the antioxidant left. In terms of mechanical and we got shear and wear. Shear down of the molecule of the viscosity index improvers. So we want to be able to test viscosity in VI as well. Make sure it doesn't change. And wear, obviously, we can take a look at the wear metal generation. Looking at a particle count, PQI, elemental analysis, ferrography, even solubles and viscosity. Great things to be testing for wear. If you don't, the consequences is lower bearing load capacity due to thinner oil thickness and a prediction of potential engine damage as well. Now with oil chemistry, chemical reactions, oxidation, nitration, polymerization, precipitation, neutralization, all these things. We can detect a lot of these things with the FTIR. And they all do bring about deposits and whatnot. One thing I want to do too, once again, not to try to sell the idea of sweep volumetry, but it's important. Polysorption and chemsorption. Here we're looking at surface reactions. Once again, loss of additives. We can actually see some foaming situations, maybe some emulsion formation, soot formation. We can take a look at these things using ICP and once again sweep volumetry. Do you know that you can use sweep volumetry to understand the anti-wear characteristics as well as the acid neutralization numbers? A lot of people don't realize that. Sweep volumetry not only tells us how much phenolics and amines are left functionality in an oil, but also we can determine acid neutralization and the functionality of our anti-wear because of the way zinc dithiophosphate operates. And dare I say, you could do the same thing with sulfonates and phenates too. Once again, phenates, sulfonates, phthalates, they're all multifunctional. They're doing different things. But we can still use sweep volumetry to understand these things. Now, so physical stress is the most important physical stress to be mentioned is heat. Pressure may be considered as well in a combination of heat when it comes to access, load carrying capabilities, and mechanical shear. This is considered by OEMs when selecting adequate viscosities. We talk about chemical stresses. Chemical stresses result from reactions caused by exposure of a lubricant to combustion gases in the following areas. Things like the cylinder liner walls and the piston rack and the crankcase interior. The chemical changes to lubricant can also work in a positive sense. Tribochemical reactions occur during the relative motions of the metallic component surfaces, which results in some anti-wear film forming. We can have physical contamination as well. Physical contamination may arise from soot, water, fuel, dust, airborne dust, and particulates generated as lubricant carries out its functions. For example, during the neutralization of the mineral acids. Now, contamination can also occur by wear particles, and that may accelerate chemical degradation through a catalytic activity. Oil analysis is used to reduce costs while increasing production and performance. We can reduce downtime, parts replacement, labor, energy, and even material costs. Oil analysis has been proven to help avoid catastrophic failures, as well as extending drain intervals, decreasing maintenance time and costs, scheduling maintenance more effectively, and increasing equipment resale value, and providing backup for warranty claims as well. There are certain problems associated with engine oils, first of which is wear. Second, being contamination, normally in the form of water or fuel, and the oil condition itself. I'm going to explore oxidation and nitration. Now, with oil analysis, the first area we're going to understand is the elemental. We're going to detect the amount of type of elements that are found in the oil, metallic elements, from component wear, contamination, various ingredients found in the oil as well. And then contamination. We can detect the physical presence of unwanted fluids such as water, fuel, antifreeze, particles such as dirt and metal wear debris, and in the oil, and identifies byproducts such as soot, nitration, and even sulfur if need be. And then the condition of the oil. Here we could test the viscosity and the oil's ability to neutralize acids, the TBN if you will, and if there's any acid buildup. There are going to be common metals found in oil. As far as the engine's concerned, aluminum, be it in the pistons, bearings, bushings, blocks, even some housings, oil pump bushings, blowers, thrust bearings, and even from dirt. Chrome, from the rings all the way down to exhaust valves, and copper, wrist pin bushings, valve trains. Iron, especially iron, cylinder blocks, cams, gears, even the liners, and silicone, anti-foam additives as well as ingested dirt. Sometimes maybe even an octane improver might get in there. Seal and gasket material, sometimes assembly grease, and sodium. It's been used as an ashless detergent in many cases. Can be found in coolant as well as road salt and sometimes ingested from the dirt. And then tin from the pistons, bearings, and bushings. There are common additives found in engine oil as well. Barium, detergent dispersant additives, the boron, anti-wear additive, even used as a marker in some cases, in smaller concentrations. And calcium, probably the greatest concentration of an additive would be the calcium phenates, the calcium sulfonates. And that's a detergent dispersion package, also contributes to the alkaline reserve as well as antioxidants. And some people even say anti-wear capabilities. And you got to find some copper in there sometimes, maybe from some European formulations. Magnesium for detergent dispersing additives and alkaline reserve, as well as molybdenum from maybe a lubricity modifier or friction reducer. And phosphorus, the corrosion inhibitor, maybe an anti-wear additive, as well as oxidation inhibitor, typically found with zinc dithiophosphate. And silicone, anti-foam agent. And then there's tin, used as an anti-wear in some cases, or friction reducing additives in others. And then obviously zinc, the anti-wear antioxidant additive, normally typically found in zinc dithiophosphate. Now, viscosity can be measured several different ways. The most common way uses a capillary viscometer to measure kinematic viscosity. Kinematic viscosity is used in finished lubricants as well as used oil. With kinematic viscosity, the capillary viscometer is filled up with oil. The oil is drawn up through the tube through suction. The tube is submerged into a constant temperature bath. And typically for industrial oils, it's kept at a 40 degrees Celsius. For engine oils and certain transmission fluids at 100 degrees Celsius. The flow of the oil is measured from a start mark to a stop mark. And that's measured in seconds. And that rate of flow between the start and stop mark is put into an equation to determine the viscosity of the oil. You can also measure the absolute viscosity. And this takes into consideration the actual shear resistance of the oil. We use an absolute viscometer here. It's also known as a Brookfield viscometer, named after the Brookfield company. In this particular test, a spindle is submerged into the oil sample. And that oil is kept at a certain temperature. That spindle is turned. The torque is measured, which is the amount of energy required to keep that spindle at a certain rate. Increasing the resistance means that more torque is required. That's a direct relationship to an increase in viscosity of the oil. So the relationship between torque and viscosity is direct. Now you can determine the centipoise, which is the absolute viscosity measurement, by multiplying centistokes, which is the usual measurement for kinematic viscosity, times the specific gravity. You can also convert centistokes by dividing centipoise by specific gravity. There's a method that's been around for a while called Sabalt Universal Second Viscosity Measurement. Unit measure here is a SUS, or Sabalt Universal Seconds. Viscosity is measured through the flow of the oil through a cup, 60 millimeter orifice in that cup, and you time how long it takes. Usually done at temperatures at 100 F or 210 F. Now here's a comparison of the three: the kinematic viscosity, the absolute viscosity, and the Sabalt Universal Seconds. Now in terms of engine oil, there's a couple other visco methods that are used to understand how engine oil perform at various temperatures. This is what's going to give it its multi-grade ability. The first of which is a cold crank simulator. This tries to understand how the oil is going to perform at very low temperatures. It does measure the viscosity as an absolute, so therefore it's going to be in centipoise, but it brings the oil down to very low temperatures. The next is a cold pump simulator. This is also going to be measured in centipoise. A little bit different apparatus though. So the cold crank, it's all about how the engine oil is performing under a journal bearing type application. But here, the cold pump simulation, well, that's about how the oil is going to pump through the crankcase and what have you at low temperatures. And a relatively new way to understand the viscoelastic behavior of the oil is high temperature, high shear viscometer. Here we're looking at how the viscosity of the oil behaves at 150 degrees Celsius under a constant shearing and high speed. All these values are going to be put into the consideration for the SAE J300 multi-grade viscosity chart. So I'll show you right now. Now here's an example of the SAE J300 chart. It was revised back in January 2015. It's going to help us understand and explain the 0W all the way to 25W classifications, and then from 8 all the way up to 60. A lot of folks don't understand what these numbers actually represent, or even what the origins are. We're going to take a quick look at this. So for instance, the 0W, 5W, 10W, all up to 25W, those SAE viscosity designations are all about the winterized effect. It's what W stands for. Now the first way in which we can qualify this is the low temperature crankability. That's measured in centipoids, as mentioned earlier. And we'll notice that those are the viscosity at various temperatures. 0W is 6,200 centipoids at minus 35. It's got to satisfy that requirement. It can't get any thicker than that. Obviously, then it won't be a 0W. Might become a 5W if that was at 6,600 centipoids at minus 30 and so forth. So that's the low temperature crank, and that's going to imitate what's going on in the bearings, especially the main bearing. We need to have flowability at low temps. So that's achieved through, obviously, some base oil technology, but also pour point depressants and whatnot, allowing flowability at much lower temperatures, so we can get that multi-gradability. But we also need to pump. So the cold pump simulator that we talked about earlier. Now all these viscosity requirements are at 60,000. You can't be any thicker than that, but they're 5 degrees more than, or lower I should say, than the low temp crank was. So when you look at 0W20, it can't be more than 60,000 centipoids at minus 40 C for that particular simulation. Now it's got to also satisfy the minimum kinematic viscosity. It can't be any thicker than those values either. Now that's for the low temperature characteristics. Now we look at operating temperatures. We're going to notice a few new numbers here, the 8, the 12, the 16. Those are going to follow the W. That's the operating temperature. Viscosity. The 8, 12, and 16s came out of Japan for the Japanese motor industry. Okay. We're going to measure those with kinematic. They're going to be a minimum and a maximum kinematic in centistokes for that range. Now we're also going to apply something new, high temp, high shear requirements. That's also in the centipoids. It's going to be done in a rheometer, another form we just mentioned earlier. But that's the viscosity requirements within that as well. So it can't be any thinner than that. Those are the minimum requirements. I'm going to take a quick look at the origins of what these numbers actually represent. So now we're going to look at the origins of these numbers. The 10 weight all the way up to the 50 weight. In 1911, the SAE published the first version of this standard. They wanted to reflect the suitability of oil used in various types of engines that were being produced, so the consumer could easily understand it and not get things mixed up. The grades were based on flow rates coming out of a cup with a hole at the bottom, much like the Sable Universal Second. So the very first grade, the 10 grade, you had to wait less than 14 seconds for it to empty out. And if you did, it was a 10 weight. And then the 20 weight, you had to wait between 15 and 24 seconds for it to empty out. If it was a 20 weight, and 30 and 40 and 50. We always think that when we say the weight of an engine oil, it has to do with WIGHT, as in mass being pulled down by the power of gravity. And that's the measurement thereof. But that's not the case here, folks. The case is that they had to wait a certain period of time. For a 10 weight, they waited less than 14 seconds. And for a 50 weight, they had to wait more than 45 seconds to empty out. So it was WAIT, not WEIGHT. Crazy, huh? What a mind blow. Now you know something a lot of other folks don't know. Something to talk about over dinner tonight, who knows? We're going to look at the changes in viscosity. Viscosity is a crucial element in engine oil, as well as understanding there's going to be a catastrophic failure emerging. But some causes for changing the viscosity is you might be actually mixing with another product, maybe thinner oil or fuel or solvent could get in there, and this can actually decrease the viscosity, or water. Thicker oil or glycol will actually cause viscosity to increase. Oxidation can change viscosity. The thermal aging, abuse, even through water contamination, will lead to excessive oxidation. This results in an increase in the viscosity of the molecules of getting larger. Soot contamination, that'll increase viscosity, thickens up the oil. Greater attention should be paid at the viscosity at 100 degrees Celsius though. And then the shearing. Sometimes you can shear down the polymers to give the viscosity index improvement. A permanent shear can sometimes decrease that viscosity as well. It's often seen. Here's a chart, some work that had been done, the viscosity versus the shear rate. If you look at the very beginning, the shear rate, the new oil pan before the screen and then across the screen, you'll see how the viscosity starts diminishing behind the wrist, behind the piston rings, and then through the camshaft and to the gears. And it isn't until it goes right back again through the cam, the tappets, and then back to used oil, we're going to actually see some permanent loss. Those polymers will shear down, but then eventually that viscosity does become stabilized. Water, well, it's a common cause moisture. It's ingression through air breathers or filters or the cover of the system, maybe a cooling system leak. And that's a big problem. Water can be a very dangerous material in your engine. It tends to rob the additives of their functionality because it is polar. It certainly does lead to an increase in oxidation, and it certainly does corrode metal as well. So water is a really bad contaminant. And you can actually either see a steady or a sudden increase in water levels as well. Depends. Water is the #1 cause for engine failures. It's oil related anyway, and #2 cause for industrial failures. It can come in several forms. It can be emulsified, where you got small droplets dispersed in the oil. The viscosity may go up. It actually starts looking like mayonnaise. And those tiny droplets of detergent engine oil can actually contaminate those industrial oils if they found their way in there too. We can have free water. Free water is the most dangerous form of water. Some people say emulsified or dissolved. It's not. It's free. Free water actually leads to a lot of corrosion and rust, and you're going to get emulsified from free water anyway. But the free water can actually start robbing your additives of their functionality as well. And then there's dissolved. Sometimes you can't even see it in there. That water can be up to 200 to 300 parts per million before you actually even visibly see it. Glycol contamination from a system, from a cooling system leak. This is a disaster because often, if this is the case, the ingression through a crack or holes in a cylinder sleeve, failed seals, gaskets, damaged cooler core, maybe improperly torqued cylinder head, all these things can lead to a coolant contamination situation where it can actually mix with the oil and then begin to polymerize and set up to where the ring and the cylinder liner actually are glued together. We can actually see this as an increase in sodium or maybe some potassium levels way before this becomes a bad problem. So we see an increase even on the small parts per million of sodium and potassium levels as a trend occurs. We're going to want to keep a close attention to our cooling system. Then there's fuel dilution. A lot of common causes for fuel dilution. It's a bad thing. It actually lowers the viscosity of the oil. Now the SAE says you can have up to 5 to 7% fuel dilution in any system. I tend to disagree with that. I don't care. I'll go to bat with this any day. I don't think fuel should be in the system at all. It's a high energy molecule. It does lower the viscosity. I don't think it should be in there at all. But they say you can get away with up to 7% supposedly, but I still don't like it. The fuel is the #2 cause of diesel engine failures for sure, especially with fuel quality. Now fuel leaks, it could be to blow by, maybe a faulty injector, leaking transfer pump seals, so forth and so on. It gets into that oil, dilutes it down. It could actually start doing things to the additives as well. And sample timing, if samples collected after extensive idling, you might have an increase in fuel as well. Cold weather startup as well. You don't have to get proper combustion. Frequent starting and or stop through trip operations. And then resampling properly would confirm if there's actually a true mechanical issue though. The question always is fuel dilution, is it dependent on ULSD or B20 fuel? There's some work that was done by Jen, Williams, Christensen, Burton, and McCormick over at the National Renewable Energy Laboratory. They found that the higher boiling point of biodiesel could result in less of a fuel evaporating out of the oil, leading to higher levels of fuel dilution, unfortunately. This particular work was done on a VW Jetta. I like to see work done on different types of engines, not just one particular engine model, but it's it's good research that was done, and I think there's more work that can be done with this as well. But the point's made is that B20 doesn't boil off or evaporate as lower temperatures as ULSD does. So therefore, it is going to stick around, and that could actually contribute to more problems as well. And remember, B20, well, it's 20% biodiesel, which is a methyl ester. That's not diesel fuel per se. It's a totally different animal. Although it does combust upon compression, it's still chemically much different. It also loves to suck up water too. So once again, we're talking about a polar situation, which is going to give us issues. Let's look at oxidation. Oxidation is a process during which the oil is transformed due to the polymerization of the organic molecules to make it up. And as a consequence, the original properties of that oil, well, they devolve. Now, increase in viscosity and insoluble compounds are seen, clogging filters and accumulating on various types of moving bits, and deposits and sediment in the engine form. You can actually get corrosive wear and the reduction of useful life of those additives as well. Now, these compounds of oxidation begin to form, and as a consequence of the oxygenated compounds, they enter into the structure of the oil. The viscosity and acidity of the oil increases. The oxidation compounds are corrosive, and they can actually form deposits which block valves and circuits and which cause equipment to fail. And this reaction is accelerated when the temperature of the oil increases. Also, many materials act as extremely effective catalytic converters in this process. For example, copper, which arises from the wear of bearings and pipes and refrigerants. The ferrous compounds formed by the action of the water and certain oxidized compounds in the oil, and various foreign materials suspended in the oil, and other products of oxidation as well. This is a view of the inside of the engine block observed from the lower portion of the block. The interior of that block is coated with dark brown and black deposits. That's a result of oil oxidation. Here's an example of an oil suction screen from a Caterpillar engine. The oxidation products in the form of some crystals actually plug the suction screen and cause a lack of oil flow through the oil pump. Now here's a particular graph of interest. We're going to look at the actual chemical reaction of the oxidation process. It starts with the initiation phase. We obviously need oxygen. That RH, well, that's just going to be our oil molecule, if you will. You see what happens though is oxygen gets on that line and actually forms a radical. That R with the dot, it's a radical. We're going to begin the initiation phase. Then we go into the chain propagation. Chain propagation, we take that radical and actually continues to react with more oxygen. And those become even more reactive, and they start to react and form bigger constituents, and then they start chain branching out. It starts cross-linking, forming a much more macromolecule. And then eventually terminates, but at this time you form a large deposit, sludge molecules, and so forth and so on. If we graph it out over time, the oxidation time it takes, we have you can see the antioxidant starts decreasing in volume, and actually the interfacial tension starts to increase, and then you can actually start seeing where catalytic acceleration occurs. And then we go through the acceleration process. Now we're starting to see an increase in acidity and a formation of these free radicals and peroxides. And then eventually it becomes completely saturated. Here's the formation of the sludge, where the molecule is beginning to become assembled. A huge macromolecule is now developed. This is oxidation. Now, one fantastic way to understand oxidation in our used oil is using the FTIR. Here we can actually pick up the oxidation peaks. We got the base peak right there. We don't see a whole lot of oxidation occurring, even nitration or sulfation that can happen sometimes with oil that's in an engine that uses a high sulfur, maybe a marine engine or a locomotive, whatever. But we can actually start picking up these things as absorbance peaks. Very powerful. You can actually take the area under that and try to establish how much concentration is in there as well. One fantastic way to understand how much antioxidants we have left in our oil formula is using a ruler method. It's a sweep volumetry. Here we have to do a baseline. It's going to be seen in the blue line right there. And our sample is red. You see there's a decrease. Then our active antioxidants are the amines and the phenols, the hinderamines and the phenolics and so forth. we actually start understanding what's useful, what life is left in our oil using a ruler test. I think the ruler test is probably one of the best tests to run to understand how much antioxidant we have, how much life we have left in our engine oils. And a lot of folks don't run the ruler on engine oil, but I think that's the neglect. I think you really should. It provides a fantastic insight into really the life left in that engine oil. Now, there's a base oil influence on oxidation as well. And some work that the folks over there had done, they published a paper on oxidation stability of lubricating base oils, Nagar and Adley and Attila and what have you. They did an oxidative study on the 3 base lubricating oils at different grades, be it light, medium, heavy oils, B1, B2, and B3 respectively. And this was studied at oxidative times of 50, 100, and 150 hours. The quality of base oils under investigation here, well, they evaluated on the basis of total acid number. They also looked at evaporation and vaporization loss and kinematic viscosity and quantity of sludge formed as well. It's a great paper. Also, the chemical composition of the study of lubricating oils is achieved via some capillary gas chromatography. They did a comparative study of the oxidative performance of the base oils and showed that the higher degrees of heavy oil compared to light, the increase in oxidation time led to an increase in the evaporation loss and lubricant viscosity. Here they actually identified that the analysis of lubricants' oxidation stability therefore contributes to a better understanding of its effectiveness under normal operating conditions and its suitability for formulating automotive lubricants as well. So the aim of this work was to study the potential life of lubricant oils inside an engine motor at different oxidative times in view of their oxidation stability. That's some pretty interesting work there. You can see where the base oil, B1 is light, 55 centistokes, and then B2 medium at 106 centistokes, and then B3 is heavy oil at 130 centistokes. There's also the relationship between metal and water as a catalytic effect on oil oxidation. This was done a while back by Abner, published this in the CRC Handbook of Lubrication. Some folks have adulterated this graph in the past, but this is actually the raw data right here. It's very interesting. He did. I take a look at the different aliquots of looking at from the clean and dry oil, and then adding a certain amount of iron, and then copper, and then even water, and see how that actually had an influence on the total acid number. And then a combination of iron and water. But it wasn't until copper and water was actually explored that we really see an incredible catalytic effect on the overall total base number, total acid number of this particular study. Fantastic. So if you can get a hands on that, that's good work to do as well. Really very interesting. It's also be interesting work to do on other types of oils and so forth and so on to see really what's going on. Be a great way to understand. Be bringing out new antioxidant chemistry to see how it reacts against these kind of things as well. There's also the reduction of zinc dithiophosphate. Now here we can actually see an increase in the amount of iron over a period of time. Now, does this have to do with a lack of zinc dithiophosphate that actually becomes compromised and used up over time? Because it's also dealing with oxidation or whatever. But it's a great graph here. This is another paper done. Tribology Letters, Volume 67, Article 68, done in 2019. Written out by Dor, Agos, Besder, Ristic, and Fascher. Engine oils in the field, a comprehensive chemical assessment of engine oil degradation in a passenger car. It's some good work, a great paper too, if you get a hold of that. We can actually see this decrease in the zinc and obviously an increase in oxidation. It makes perfect sense. Zinc dithiophosphate, not only is it acting like an anti-wear, but it's an antioxidant as well. We can actually understand why iron would start building up. Now, nitration. Nitration is of concern in many engine oils, particularly natural gas engine oils, but we see this as well as diesels. Now, heat can cause atmospheric nitrogen in the form of N2 and oxygen to react, forming nitrous oxides. And these nitrous oxides interact with the lubricant by creating organic nitrites. And by picking up as either soluble or insoluble nitrous compounds, now nitration can cause premature thickening of the oil. And common causes of this could be inefficient exhaust of the combustion products, or improper air to fuel ratio, low operating temperature, maybe leaking piston seals. Some advanced timing issues as well. Early combustion will increase nitration. And biodiesel use. Without the proper adjustment to the timing, biodiesels can produce more nitration than conventional diesels at the same settings. Here's a picture of some nitration. You notice that the orange, dark brown if not orange, causes this deposits, especially on cool parts of the engine, such as piston skirts shown below. So it's all about thermal management as well. Here's another example. The oil nitrations created a brown sludge is observed on top end of this engine head. It does have an orange hue to it, though. That's where usually you can tell. Now, soot, common cause of soot. We have retarded timing. Late combustion will increase soot generation and fuel consumption. It correlates with the increase in viscosity. Soot is nothing more than unspent fuel. It's just fuel that hasn't gone through the complete combustion process. If you have complete combustion, you should only be giving off carbon dioxide and water. That's never the case, is it? Combustion engines are ridiculously inefficient. But we use them because we have a very cheap source of energy to power them. Otherwise, I don't think a combustion engine would ever be built. You can have overfueling. Faulty injectors may actually cause soot to increase, and that'd be evidence of detection fuel. And then poor airflow. Increased air intake or exhaust leads to soot generation. Requires some visual confirmation. Question always was, in fact, Fred Rounds did some great research on this years ago. He presented this at a STLE conference many years ago, and people always thought soot was abrasive up until this guy came around and actually proved them. That's not necessarily abrasive. Actually, it's kind of interesting. I'll read it to you. The combustion-generated soot in crankcases of diesel engines can significantly increase engine wear, valve train, and liners. This is caused by the diesel soot absorbing the anti-wear additive in the oil. So these things obviously have polar nature, and they do absorb the additives. So tell me the correlation versus cause and effect. What's the difference? Well, here's a perfect example of this. Okay. Soot can also be fuel dependent. Here we look at ULSD versus the B20 again. Once again, it has to do with combustion properties. We want to look at the total base number, total acid number. This is done through titration. We're going to always count the milligrams of KOH or HCl. In this case, potassium hydroxide. It's always reported in milligrams of potassium hydroxide. Even though in the case of a base number, we're titrating in acid, we're still going to report in KOH. I'd love if someone could tell me why we do that. I know there's a really good reason, but I've never met anybody that tells me why it has to be done. If we're titrating HCl, it converts back over to KOH. Well, I don't know. It just, to me, the whole thing needs to be all revamped. Anyway, so we know that more drops of HCl produces a lower TBN for gasoline engines. More drops of KOH produces a higher acid. So both mean lower remaining oil life. So the lower the TBN, less life it has. The higher the acid number, the less life it has. It's usually determined in oil change intervals in gasoline, natural gas, and even diesel engines. When we take a look at the base numbers and acid numbers, oils, depending upon the chemical constitution, the additives there, they may exhibit some apparent acid and or alkaline reactions without any free acid or alkali actually being present. And fresh diesel engine oils may show an acid number around maybe 1 to 2 KOH per gram, depending upon the brand. It's generally considered that the increase from an initial figure of the tan is either the indication of contamination with maybe an acidic combustion product or the result of oxidation. But in the case of oil oxidation, other evidence is generally available, such as an increase in oil viscosity. Now, the weak acids formed when oil is oxidized, they don't necessarily attack ferrous metals or even white metal, but it can cause corrosion on copper and lead bearings as well. Now these materials, they're generally oil soluble. The oxidation products formed, they contain oil soluble carboxylic acids that are extremely corrosive towards lead phase and even copper lead bearings. Now potential bearing corrosion problems cannot necessarily be inferred from the tan of the used lubricant per se, since the acid tetracate method can't really distinguish between corrosive and non-corrosive acids unless you take a look at the graph. You just have to, and nobody does. They should. A lot of folks don't do it with the tan. You can take a look at actually how the graph proceeds, and then you can actually start dissecting out what is strong and what is weak acids. You can also do this on the ruler, by the way. A lot of people don't realize this. You could do it. You can actually establish a total acid number on the ruler and detect what is strong acid and weak acid. Should that oil show a strong acid number, that's a strong acid, significant risk and a problem for sure. Now some common causes. Normal operation results in a steady rise in acid number until that oxidation inhibitor is depleted. The increase becomes exponential and correlated with a small viscosity increase as well over time. Now we want to do trending. Often the trend of an acid is greater importance than actual value itself. The problems of dilution here, though. Large volume reservoirs dilute changes in acid number. So the rule of thumb, when an acid number is double its new oil value, it's probably time to change that oil. It's not a bad rule of thumb. Some people will challenge it, but sometimes you're better safe than sorry in this case. The exception might be in natural gas engines. A lot of times folks out there say that there's require a change. If it starts out at about a 1, if it gets up to be a 4 or 5, then it should be a change. With base number, there's a reduction. There's many causes for this. Many causes for reduction in the base number. The high sulfur content, the fuel, that can do it. Very low oil consumption, insufficient fresh oil top-ups. Maybe low cylinder liner temperatures as well. Maybe ingress of drain water condensed in the air cooler, ingress of water due to improper design and intake vent. Other general water contaminations can do this too. Remember, these water is very polar. Low load operation, cold operation, bad combustion, neglect of fresh oil top-ups, or maybe you're topping up with a low base number. Well, the other thing too is always maybe you have excessive blow-by in the crankcase, raw residual fuel contamination, dilution of lubricating oil. These all things can cause a reduction in the base number. So things to consider: high temperature. Elevated temperatures will result in a dramatic increase in acid production. That lowers your base number. The water content, that'll contribute to a greater acid production as well. That lowers your base number. Not every application measures additive performance rather than by byproducts of oxidation. Therefore, oil must contain a base number additive, right? Typically, only diesel engine oils do, though. Some gas and natural gas engines do, obviously. There's been a push a little bit to go towards some other products that companies are actually starting to look into using an acid neutralizer for things like hydraulic fluids, especially universal hydraulic fluids. And I've heard tell that there's some folks that are doing this with gear and transmission fluids as well. They're really trying to push for the lube to life, and this is one way they do it. Increase the cost a little bit, but according to some data they found, it might actually help. Now, there's different ways we can actually test for alkalinity reserve. We got the acid solvent measures, examples in fresh oil, examples in used oil. Here, for instance, in new oil, they use a perchlorate and glacial acetic acid. Chlorobenzene as a solvent with glacial acetic acid. It's going to measure strong acids and weak bases, strong bases and weak bases for all detergent bases and all dispersant, even amine bases. So they'll look at the magnesium and the calcium and the salts of degradation products. Now, used oil, that's where they use the HCl. Now, this is going to measure strong bases and some weak bases as well, but mostly strong bases. This is why we typically want to make sure we're using the 4739 for used oil. You don't want to use the 2896 for used oil. That's for new oil. A lot of times there's companies out there that play games with that, and that's just not right. I mean, we're trying to have data here that means something. So if there's some people who put the used oil in for $28.96. That's really relegated for new oil dig. You know, that's just not cool. And then there's the 664. That's an obsolete method.
I think that is the end of the presentation. I'd like to thank you all for attending. It was a bit of a longer one. And yeah, like I mentioned, Michael wasn't able to present live for us. But if you do have questions regarding the tribology of combustion engines, please definitely let us know. You can provide the questions in the Q&A, or if it comes to you a little later, definitely you can, Michael's included his email address on here as well, and you can give him a call, or you can email him and contact him. So I'd like to thank everyone for attending. As always, questions, contact us. Otherwise, you guys have a great day. Thank you.
Thank you. Bye-bye.
Yeah.